Hey yo, what's up, science fam? It's your boy Nickel here. All right, now we're gonna start by just identifying and describing Earth's atmosphere. Now we have done a little bit, and we've talked a little bit about Earth's atmosphere earlier on in the school year, but as you guys should know at this point, it's basically just a layer of gases that surround the surface of the Earth. So let's record that here. It's a layer of gases that surround Earth's surface. Now, it is composed of essentially three types of gases. There's a lot more than three gases, but a majority of the gases are actually just two of the three gases, and that is nitrogen and oxygen. The third most abundant gas is a gas that's inert, meaning that it doesn't really cause much of a reaction with any other things in our atmosphere or with, luckily, us as humans or any other species, and that is argon. If we actually look at the percentage of nitrogen in the atmosphere, we have roughly 78.1% nitrogen. We have roughly 20.9% oxygen, and less than 1%, 0.9% of our atmosphere is argon. Now, let's write what the chemical formula for nitrogen would be. Nitrogen is going to be two nitrogen molecules that are attached together, and so we'd write N2 because there's two nitrogen molecules. Oxygen, interestingly enough, is very similar, where there's two oxygen atoms that are connected and bonded together, and that is an oxygen molecule, so we do O2 because there's two of them. Argon is just simply an element by itself that's floating in our atmosphere in the gas form. And if you were to add all this up, we'd actually be short a little bit of 100%. So the rest of our atmosphere is really just 0.1%. That's the remaining amount. And the remaining amount contains a lot of rare gases, as well as our carbon dioxide and our methane. So we hear a lot about methane and carbon dioxide and how those concentrations are increasing in our atmosphere. But really, if we look at all of our atmosphere, it's only 0.1% of our atmosphere. And so, therefore, it's a very, very small amount, but it's really, really important in the atmosphere. So if we were to write the chemical formula for carbon dioxide, we could write it here as CO2 because it's two oxygens bonded to a carbon. And then methane is a carbon with four hydrogens bonded to that carbon. So here we have a general idea of what our atmosphere is composed of: nitrogen, oxygen, argon, some rare gases, carbon dioxide, and methane as well. Now, our atmosphere is not only one layer, but we can actually break it down into multiple layers. So let's draw ourselves a diagram here at the bottom of the page. So we'll first draw the curvature of the Earth to draw the surface. Now, the first quote-unquote layer is going to go from the surface. Let's draw a line here up, and we'll say that this is it's roughly 10 miles up is where we're going to find our first layer. And this first layer is called the troposphere. And the troposphere, it's where weather occurs. So in order to show that weather occurs here, I'm going to draw a cloud, maybe some rain as well. This is where all of our mountains are as well. If you were to climb a mountain, you're never going to leave the troposphere, even if it was Mount Everest. All right, now from that very indistinct line, because there's not really a line in the sky, but from 10 miles up to about 50 miles up in the sky, This region is called our stratosphere. And this, in the stratosphere, is where airplanes fly. And they fly pretty low in the stratosphere. So I'm going to draw an airplane down here to show that a lot of us have been up in the stratosphere, but hopefully you're in an airplane when you got up there. Now, another important thing that is between 10 and 50 miles up in our atmosphere, between our troposphere and it's within the stratosphere, is a layer that maybe you've heard of, and it's called the ozone layer. And the ozone layer is between 20 and 30 miles up in the sky. So the ozone layer stretches all the way across our Earth. And the ozone layer is super, super important for us here on Earth. So I'm sure you've heard of putting on sunscreen before, and the reason that we put sunscreen on is to protect ourselves from ultraviolet radiation. But without the ozone layer, we would have a lot more ultraviolet radiation, maybe even so much that it could harm life on planet Earth way more than it does, because the ozone layer actually blocks let's just say it blocks most of the sun's UV light. So most of the light comes through our atmosphere, hits the ozone layer, and it bounces off. Some of it does get through, and that's why we still need that sunscreen, but the ozone layer is really, really important. I'm just going to shade that in there to show that it's right about there. Okay, so we have ozone layer, which is within the stratosphere. The stratosphere is on top of the troposphere. Airplanes fly in the stratosphere. If you go above the stratosphere, 50 miles to about 85 miles up, this here would be considered the mesosphere. And above the mesosphere, we have the thermosphere. Now, if you keep going up, there's actually an area that's called the exosphere. And in the exosphere, two molecules of air actually would never really run into each other because they're so spread out. So really, when we talk about air density, this air way up in the thermosphere and the mesosphere and the stratosphere, this is all really, really sparse, meaning that it's not very dense. Now, the thermosphere would be the least dense, the mesosphere is going to be the more dense than the thermosphere, stratosphere is more dense, and the troposphere is the most dense layer. So when we look at actually where the types of gases are in our atmosphere, the ones that have more molecules like carbon dioxide and methane, those are all going to be lower and closer to the surface. The ozone layer is made out of ozone, and let's just write over here that the chemical formula for ozone is O3. So it's actually 3 oxygen molecules all bonded together. So that ozone layer, like I said, is super important. All right, so this is the structure of our atmosphere. If we were to be able to zoom out and like diagram the actual layers that we have. Let's look though at how these different layers in the atmosphere are responsible for making our planet habitable and making it a nice, warm, beautiful place. So to do that, let's turn to our next page. And on this next page, we're going to draw a model of Earth in the solar system. So I'm going to draw a sun here, and it's going to be a sun that's small because it's symbolizing the fact that it's far away. Now, the sun is emitting energy. It's emitting light energy, and we know that because during the day it's nice and bright outside. But also, as you stand in the light of the sun, you can also feel heat as well. So another thing too is if you stand in the sun for too long without sunscreen, it will actually burn your skin, and that's because of the ultraviolet radiation that's also being transmitted from the sun. So far off in the distance we have the sun. Here we'll draw planet Earth, and we'll draw a bit bigger than the sun, quite a bit bigger, because this will be more in the foreground here. And if the sun is over here, then I'm going to actually shade in part of the Earth, because this backside of the Earth would not have any light on it. So since it doesn't have light, this is a dark portion of the Earth. This portion of the Earth would be what we would consider to be nighttime. All right. Now, our North and South Pole are not directly straight up and down on our Earth. It's actually, our Earth is tilted just a little bit. So I'm going to draw some lines here to show where the poles would be here on our Earth. And that angle, actually, let's draw a little diagram to show what that angle would be. The angle of Earth angle of Earth's tilt is equal to 23.5 degrees. So that's just tilted 23.5 degrees. And actually this tilt means a lot. Before we finish our picture here, let's just quickly draw a model of why that tilt is so important. So if I have my sun here, and my sunshine is constantly shining with the same amount of brightness all the time. But as the Earth goes around to different points, here, if we were to take this tilt of the Earth and apply it over here to my little model of the Earth, then the Earth would be like in this direction. If we think about the equator, you can see the area above the equator is pointed just a little bit closer to the sun. So therefore, since it's got more direct sunlight, it'd be summer. And in the southern hemisphere, it's facing away from the sun, so it'd actually be winter. Now, as the Earth continues around in its orbit, when it gets over to this side, the tilt is going to maintain the same angle. So now if I draw the equator, now the northern hemisphere is tilted away from the sun, so that is now going to be our winter, and the southern hemisphere is going to have their summer. And that's why the summer and winter seasons are opposite, depending on which side of the equator you're on. So to make a key here, S means summer, and W means, you guessed it, winter. Okay, so here's some extra information, but let's get back to our diagram here that we were drawing, this model of the sun and the Earth. Now, like I was saying, from the sun, when it is daytime out, as we all know, we can see because there's visible light, and the light bounces off of things and bounces into our eyes. So if we draw from the sun, we're going to draw some light waves coming to the Earth, and we're going to do them like this because light travels in a wave. I'm going to draw an arrow there to show that this visible light is interacting and hitting the Earth. Now let's label this visible light. Now there's other types of energy that's coming from the sun across space and hitting the Earth. And another type of that energy that we're going to show right now would be ultraviolet radiation. Now we can't see it, and so we don't really call it light, we call it radiation, but it's still just some energy traveling from the sun. But you can see the way I drew it with energy waves that are much closer together because ultraviolet radiation has more energy, and that's why it can burn our skin. Ultraviolet radiation. Now we could call it visible radiation, but we call it visible light because we can see it. Ultraviolet radiation, it's very similar to visible light. It's actually in such a fast wave or a small wavelength that we can't see ultraviolet radiation. But some things can, like for example, honeybees can see ultraviolet radiation. So all of this energy is hitting the Earth, and so therefore we could say that Earth's heat, the heat of our planet, increases due to absorbing energy. So it's absorbing the energy from the sun. The sun is transmitting it in the form of visible light and ultraviolet radiation. Okay, so let's kind of summarize that down here and say that let's say the energy is absorbed as, and as we already said, visible light and ultraviolet radiation. The energy that's absorbed, the energy is released then after it's absorbed. If we are absorbing a lot of energy, well, we can't just store energy. The Earth will eventually release that energy. So the energy is released from Earth, or from the materials on Earth's surface. The energy is released from the materials on Earth's surface as a different type of radiation. And this is as infrared infrared radiation. So when you stand next to a fire, the reason you feel that heat is because that energy from the wood is being released in the form of infrared radiation. Okay, let's draw ourselves a model then to tie all of this together. That the fact that visible light, ultraviolet radiation hit the Earth, and then the Earth releases infrared radiation. So to do that, we need the curvature of the Earth, the sun way off in the distance is transmitting visible light. So we'll say visible light arrives here, and also ultraviolet radiation, which has a shorter wavelength and has more energy. So we draw a line that looks more with the crests and peaks of the wave. Actually, the troughs and the peaks are more closely together for, we can just write UV radiation. So all this is being absorbed by the Earth. And we know different materials absorb it differently. So if there's a big ice patch here, probably wouldn't absorb as much, it'd reflect more of it. But if it were like a pavement, parking lot, it's going to absorb a lot more of this type of energy than it would if it were something that is more reflective. So that is absorbed, and then our Earth actually releases the heat. And you've probably felt this before, that after the sun goes down, you can go across a parking lot and you can feel the heat radiating off of it. Or for example, if the fire is out and you get close where the coals are, you can still feel some of that heat coming off of the coals. And so keeping in mind that we drew these waves coming into the Earth with a certain type of design, infrared radiation that leaves the Earth. So infrared radiation can be abbreviated as IR, infrared radiation, or infrared. Those are longer wavelengths. And so those longer wavelengths are going to be really, really huge. And so it almost looks just like a lumpy line. And that infrared radiation then leaves the Earth in that format. So it comes in high energy and it leaves in this low energy format known as infrared radiation. And this is actually how heat is transferred, mainly through infrared radiation. So the light energy heats up the Earth. The heat from the Earth then is released into the atmosphere through the format of infrared radiation.